of potential energy is the change of potential energy equals the work done by conservative force with a minus sign. Only the change of gravitational potential energy matters. The exact value of potential energy doesn't matter because only the change corresponds to work, and work is the thing that actually changes the kinetic energy. Let me just give you an example. If you have something that starts with 0 kinetic energy, you release it from rest, and then as it drops down, you get some speed, and your kinetic energy goes up. Alright? Now, there are a lot of ways you can say what is, you can name the value of potential energy. You can say the potential energy at here is 0. That's totally fine. As long as you keep track of the difference of potential energy. If your height decreased by h, let's say it dropped down by height h, then your y position will decrease by h. So your potential energy should decrease by mgh. Therefore, if you say your potential energy at here is 0, then your potential energy at here will be minus mgh. Okay? The only thing that matters is the difference of potential energy. You can set 0 to be anywhere as long as you keep track of the difference. So alternately, you can say it should be final. You can set the potential energy at here to be 0. You can do that as long as you keep track of the difference. If I set the potential energy at here to be 0, then the potential energy at here should be higher because the height of the ball is at height h higher than the height down here. So if your height is h higher, your y position will be h higher, and your potential energy should be mgh higher. So if I set the potential energy down here to be 0, what will the potential energy up here be? mgh, yeah. It needs to be mgh higher. You can see the potential energy decrease by mgh. Same with here. The potential energy decreased by mgh. The difference of potential energy is the only thing that matters because that's the only thing corresponding to the work done by the conservative force. Therefore, the exact value of potential energy doesn't matter. You can say the potential energy of the ball here is 0, negative 10, negative 100, doesn't matter. As long as you keep track of the difference, you'll get the same value. I'll show you, I'll prove it right now. Let's say we want to solve for the speed of the ball when it drops down for a distance h. Then the final, so energy is conserved because there's no air resistance. Let's write out the equation again. The work done by non-conservative force will change your total energy. So if this is 0, then your energy is conserved, which means the initial potential energy plus initial kinetic energy equals final potential energy. I should write it in reverse, which means the initial kinetic energy plus initial potential energy equals the final kinetic energy plus the final potential energy. That's energy conservation. So if I set the potential energy up here to be 0, then both the initial and both the initial kinetic energy and initial potential energy is 0. I get 0 plus 0 should be the final kinetic energy. Kinetic energy is 1/2 mv squared. We need to memorize that. And the final speed is just v. So I get 1/2 mv squared as my final kinetic energy. And my final potential energy, if I set the potential energy up here to be 0, will be minus mgh. So this is what I get if I set the potential energy up here to be 0. Okay? Alright, now if I set the potential energy down here to be 0, what will be the initial kinetic energy of the ball? What is the initial kinetic energy of the ball if I set the potential energy down here to be 0?
Is it 0?
Yeah, it's 0. It doesn't, it's kinetic energy. How about the initial potential energy? What is the initial potential energy up here if the potential energy down here is 0?
mgh.
Good. Now, what will the final kinetic energy be? Kinetic energy is 1/2 mv squared. If I set the potential energy down here to be 0, the speed down here is still v. So what will be the final kinetic energy of the ball? What is the final speed of the ball?
V.
So what is the final kinetic energy of the ball?
Is it also v?
1/2 mv squared. Does that make sense? Kinetic energy is 1/2 mv squared. So the final kinetic energy is 1/2 mv squared. Changing the 0 point of potential energy will not change kinetic energy because kinetic energy is kinetic energy, potential energy is potential energy. They are different. Kinetic energy is only related to the mass and the speed squared. Okay?
So the speed, the final speed was different.
The final speed is defined as v.
Okay.
I'm analyzing the same process with different potential energy. I set potential energy to be 0 up here or down here, and I'm trying to show you that it doesn't matter where I set it to be 0, as long as I keep track of the difference of the potential energy, I should get the same answer. Okay? Now, here I am setting the potential energy down here to be 0. So what is the final potential energy of the ball?
0.
Good. And if you look at what I get from these two different values of potential energy, this tells me 1/2 v squared because, alright, this tells me 1/2 mv squared equals mgh because when you move mgh with a minus sign to the other side, you get rid of the minus sign. And here, it also tells me 1/2 mv squared equals mgh. So you see the result will be the same no matter where you set the 0 point of potential energy is at. The exact value of potential energy doesn't matter because only the change of potential energy matters. As long as you make sure that the potential energy down here is minus mgh smaller, then you'll get a same answer. It's up to you to say what's the value of potential energy of the ball down here. It doesn't matter. I can say the potential energy of me right now is 100. That means nothing. Or I can say I have negative energy because my potential energy is negative 100. It doesn't matter because the only thing that matters is the difference of potential energy. Okay? I can even say the potential energy down here is square root of minus 1. You guys learned imaginary number before? Good. I can say potential energy down here is imaginary. Then the potential energy up here must be mgh higher. So it's a complex number. It's square root of minus 1 plus mgh. It doesn't matter what you call the potential energy down here is, because if you say square root of minus 1, then the initial potential energy becomes square root of minus 1 plus mgh. And the final potential energy becomes square root of minus 1. And you'll see after you subtract both sides by square root of minus 1, it cancels, so it doesn't matter. Okay? The exact value of potential energy doesn't matter because only the chain of potential energy corresponds to the work done by the conservative force. And the work is the only thing that truly affects the object's motion. Alright, good. So they both give me 1 half mv squared equals mgh. I can cancel the m, move the 2 to the other side, and get v squared equals 2gh. So the speed of the ball after it falls down will be square root of 2gh. Okay? You can run a dimensional analysis and see this is indeed length over time. You can run a tendency check. If you start with a higher height, the speed when you fall down will be faster. If you are on a fan with bigger gravity, then the speed when you fall down will be faster. Okay? So that's how we use energy conservation. And the key is that you are just naming the work done by conservative force as minus the change of potential energy. So do not double count. Don't double count the work done by conservative force.